All right, welcome back, everyone. It appears that we are now live. And today we are going to be counting compositions. And this is once again going to be a randomized algorithm. And yes, it's a bit of a spoiler alert to say that we will again be invoking Schwarzschild from a couple of miniatures ago to get to where we want. But let me begin by telling you about the problem that we're interested in today. So we're going to be dealing with permutations. So permutations are just bijections, let's say from 1 to n to itself. And we're going to be using this array notation because that's what the miniature apparently found convenient. Think about permutations is that there are many different ways of denoting them, and different people have their favorites. The array notation is, I guess, it's one convenient way of doing it. So you assume an implicit indexing, which is 1, 2, 3, 4, 5 in this example. And so if the array says 2, 1, 5, 3, 4, the way to read that as a permutation is to say that 1 goes to 2, 2 goes to 1, 3 goes to 5, 4 goes to 3, and 5 goes to 4. So think of the implicit array index, which I have not written out, as being the domain. And the number that is sitting at that index is being the range of the permutation. Well, I mean, the domain and the range are both 1 to 5. What I mean is think of the guy sitting at the ith index is the value of sigma 5. Sigma is the permutation. That's one way of denoting a permutation. I think some people call this the one line notation, some people call it the array notation, whatever. So yeah, and these are, I don't know if it's helpful, but a couple of pictures also showing bijections. So think of the left as the domain 1, 2, 3, 4, 5, denoted by 5 colors, and then the arrows tell you where they map. So in this example, I think it's the same as the picture on the left is the same as the example below. So 1 goes to 2, 2 goes to 1, and then there's 3 goes to 5, 4 goes to 3, and 5 goes to 4. That is, of course, reading these guys as maybe I should have written this out explicitly. I always realize these things when I've started talking. So yeah, think of these as 1 to 5. And then hopefully it's all consistent with what's below. The permutation on the right turns out to be the inverse of this permutation. And one way to check that is imagining that you apply one of these permutations first and then compose it with the other one, that is, apply the next one on top of it. So one way of thinking about that would be to say, well, let's see. We know that 1 goes to 2, right? And here we ask ourselves, well, where does 2 go? The second chap takes 2 back to 1. Look at 2. 2 goes to 1 here and 1 comes back to 2. So you can think of it as, if you like thinking physically, you can think of this function as swapping 2 wires and this guy unraveling them. So yeah, so this is a swap that just got undone by this permutation here, by just applying it again. It's the same permutation, but by applying it twice. It's the same permutation localized to the first 2 elements, but basically by applying it twice, you have undone the effect of the first one. Let's look at what's going on the last 3 elements. What we have is, well, 3 goes to 5. So let's look at where 5 goes back to 3 here. 4 goes to 3, and 3 goes to 4, right? And 5 goes to 4, and 4 goes to 5. So if you applied these 2 permutations in succession, one after the other, compose them with each other, then you would essentially recover the identity permutation. And that's basically the definition of an inverse, which is to say that the inverse of a permutation sigma is another permutation pi, such that if you were to apply pi first and then sigma on top of it, or the other way around, you would basically end up with the identity permutation. So does that make sense? Does all the terminology that we've introduced so far kind of fit? Are there any questions? Okay, thank you. I will take that as a sign to move on. So here's what we want to count. Given a set of permutations, we want to count the number of permutations that are generated by composing these pairwise. So do this for all pairs of permutations in P. P is a collection of permutations. So pick any pair of permutations. And in fact, we're going to do this for all pairs. But yeah, so for each pair of permutations in P, compose them to get a new permutation. And that new compose them to get a potentially new permutation. It need not, strictly speaking, be a new permutation. For example, if one of these permutations was identity, then you'll just get back the other guy. So in some cases, you may not really be generating a new permutation, but sometimes you might be. So in any case, the idea is to collect all of them, not with multiplicity though. If you see a permutation that you already have, this doesn't count. So this is a set, it's not a multi-set. And we want to count the exact size of this set. So let's just think about, how large can this set be and how small can it be? Okay. Suppose P has, I don't know, let's just, like, for convenience, fix a number. Suppose P has some 5 permutations of 1 to n. We don't have to fix n. Well, certainly P composed with itself has at least 5 permutations. Is that clear? I mean, in some sense, the number of pairs that we are considering is 5 times 5. There are 5 choices for sigma, 5 choices for tau, right? And we haven't said that they're distinct necessarily. So the number of pairs we are going over is 25. But this set may not have all the 25 elements because you may have collisions. Some things may end up being the same. So you may not see 25 elements. But hopefully it's clear that you see at least 5 because when the permutations are the same, I guess, okay, so I was going to say it's easier if P had the identity permutation because then you would generate P itself. A permutation composed with itself is not necessarily, okay, so if P doesn't have identity, I don't know if it's clear that there are at least 5 permutations. Is it clear that in general, I want to say that there's at least size of P many permutations in this set? Is that under the assumption that identity is in, it's kind of obvious. Otherwise, okay, I don't know. I don't know if the permutations are all distinct, if we can be sure that when the permutations compose with themselves, they will also end up being distinct. Okay, maybe if somebody has a comment on this, that would be great. Otherwise, we can circle back to it. But certainly no more than 25 in this example when P has 5 permutations. In general, no more than size of P squared, because that's just how many things we have to generate the set. So you're not looking at more than size of P squared. But it can be as small as the size of P. You can have a lot of stuff getting knocked out. So in particular, if P is the set of all permutations to begin with, then there's nothing new to generate. So the size of P composed with P is going to be just P itself. More generally, if you have a subgroup of the permutation group, then you're not going to see anything new because subgroups have closure. So when you closure under composition. So if you compose things from a subset of permutations, which is a subgroup, you're not going to be generating anything new. So that's one extreme where it can be as small as the size of P. At the moment, I don't know if it can be any smaller. I don't think so. Certainly, if identity is in there, it's not going to be any smaller. But in general, I think that's still true. But I don't have an immediate argument for it. But anyway, the point is that it need not be as large as size of P squared, although that's kind of the upper bound. And you can probably think of examples where it does get pushed all the way to the size of P squared. But in general, the size of the set can be anything in between size of P, potentially even less, and size of P squared. So that's the range for the size of this set. And that's our goal. We want to determine how many elements are there exactly. And what's one way to do this is to just generate the set, right? So you have the set P. You could even write a small script quite easily, which just does like 2 nested for loops, right? And goes over all choices of sigma and tau, does the composition, checks if this permutation is already in the set or not, right? And if it is not already in the set, then you add it. Or you could just generate all the permutations and then write them in array notation, right? Write them in array notation and then sort them like words, and just do one pass to deduplicate this list. So you could do that too. And all of this will take roughly, how much time will this take? The nested for loops there are n squared options. Well, not n squared, actually, size of p squared options to go over. So if you have m permutations in this list, that's the brute force approach is m squared things. And then you have to compute the composition. So what does that take? Well, I think even an array notation, that's going to be, I think, linear time, right? Just apply one function, apply another one. So that's, let's just say, linear time. And then at the end, you'll have to take the list of everything that you've generated. So you've generated m squared objects. So you'll need to sort them, right, to do the deduplication. So that's the overall time that you've spent doing all of this. And I suppose we want to know if we can do better. So this is the goal. The baseline algorithm is the brute force. Let's just generate everything. And I think what I had here is an example of what that might look like. So here is here's a set of permutations. This notation is probably not very helpful, but let's say we have 1, 2, 3 is green, blue, orange in that order, and these are all now permutations in array notation. And you can just, so this is what I did. I just computed for each pair of permutations their composition. And I think it's okay, I've already forgotten, but I think it's the row getting composed with a column or whatever. So you generate a bunch of things. I will not bore you with the details of this example, but hopefully it's largely typo free. Okay. And it turns out that here I have a set of 3 permutations over the set 1, 2, 3. And there are 6 possible permutations of 1, 2, 3, right? There's the identity, there are the 2 cycles, and then there are 3 that you get by keeping 1 point fixed and swapping the other 2. It turns out that when you take the composition set for this set of 3 permutations, you actually end up generating all the 6 permutations. So of course, I said in general, this can blow up to size of p times size of p, but you really, it's basically min of that and n factorial, right? Because I cannot generate more than 6 permutations. And now, yeah, that's basically, this is an example where it blows up as much as it can. And I think, okay, I think Jagdish is pointing out that, okay, by relabeling, I guess we can assume that something like just call one of these things identity. And does that make sense? I suppose that's reasonable. And okay, and Janki has an alternate argument for why we have at least p permutations that does not involve relabeling. I think every permutation is a collection of cycles. That's fair. Now, for any permutation, t squared is the graph obtained by adding an edge between 2 vertices exactly distance 2 away. And the set of vertices in each cycle is preserved. Okay. Okay, so you're saying that, the base permutations should not collapse. Let's see, is that so what are the vertices of your graph, Janki? Maybe I'm missing something here, but are the vertices 1 to n, the set of things that are being permuted?
Yeah, hi, can you hear me?
Yeah, we can, yes.
Yeah, so I was just saying that you can look at it as cycles. So suppose 1 goes to 2 and 2 goes to 3, then in the composition 1 will go to 3.
In the composition of this permutation with itself?
Yeah.
Oh, I see. Okay. Okay.
So like just for t square, like since t's, the
Yes.
t's are distinct.
Right. Okay. So what you're saying is when you compose a permutation with itself, the basic cycle structure is preserved. So in terms of components, the like sigma composed sigma will be the same as sigma. So if we had 5 distinct permutations to begin with, they will all still be preserved when we do.
No, I think there is a mistake in the argument. Sorry. Yeah, sorry.
Okay. All right. No worries. I think, yeah, I'm not, yeah, okay. I mean, yeah, pending verification, I guess. But yeah, I mean, I have a feeling that that there's a natural choice of, yeah, I mean, it feels like the sigma composed with sigma taken over all sigmas and p should all be different permutations if all the sigmas were different, which they are. But I don't know if we can combine this with what Jagdish was saying about treating one of the sigmas as thinking of one of them as identity by relabeling. I think that also makes sense at a certain level, but I just have to parse that a little bit to be sure. But yeah, okay. I mean, yeah, this is not something that really. I mean, we don't need a lower bound on the size of the set. We're just going to try and come up with a way of figuring out what the size of the set is. So we don't really need it, but it'll be good to know that this is indeed a fair lower bound. So I think the relabeling thing makes sense. We'll have to think about how the structures of the cycles go when we do compositions. I think it's a nice start. And so Janki, will see if we can build on your idea and when we circle back to this. Yeah. Okay, all right. So give me a +1 if the brute force approach makes sense. And if you can see that that's, well, a time-consuming affair in terms of where we have the n squared choices for each, n squared choices or size of p squared choices. And for each of those, we need to spend some time computing the permutation composition. And then once we are done at the end, we need to also spend some time. We have a bunch of m squared things, and we have to deduplicate this list to make sure that we have an accurate count at the end. So one way to do that would be by sorting, but yeah, all of that takes time. So let me know if the baseline approach is clear so that we know what we're trying to improve upon. So give me a +1 if the brute force is okay. All right, cool. Thank you. Perfect. So moving on. Yeah, the question we always ask ourselves is, can we do better? And it turns out in this case.
And by the way, you don't have to sort the thing.
Okay.
You just have to hash it, right?
I suppose so. As you go along, you could just build it out as a set. Is that
No, you can just have to hash it. If two people collide somewhere, that is fine.
Right. Yeah, I think that's fair.
Okay.
I mean, yeah, I think that's fair too. I mean, yeah, if I was probably just didn't know what would be the exact. So
yeah, I mean, I'm assuming that the overall, your claim is that we don't have to look at all n square.
Yeah, well,
right?
yeah. So also, I think, I'm not sure if I should just put this somewhere at the top in terms of notation. Let me say that m is the size of p, and we're looking at permutations over n. So just to distinguish between m and n, so we could be dealing with a pretty large set relative to n, but they're all permutations over n. And so we have m squared times n just to compute all of these composition pairs, right? And let's see. Yeah, I mean, even if we don't, so yeah, one idea was and I don't know if, so whenever you say we're hashing, as we generate these permutations, we only add them to the set if it's fresh. So you could just basically do a set union at every step. Is that
yeah.
Is that what you're hinting at? Yeah, perhaps that's doable too. Saves you the explicit deduplication at the end. But for some reason, that's an idea that was mentioned in the miniature, so I thought I should also.
Anyway, it shouldn't matter. Yeah, it probably is that we shouldn't take more than m square steps. Yeah.
Correct. And now I'm just okay. I remember that I had not made explicit the running time of the of the algorithm that we do come up with. So that's something that we'll have to do as a crowdsourced exercise, and we'll come back and check if we have improved on this. But yeah, I mean, the bulk of the time is really M squared n in just computing the objects. And now whether you do an explicit deduplication or you just hash on the way, yeah, that's probably not where the main overhead is coming from. So, okay. All right. So you're going to try and see if you can do faster. And again, what we are going to do is, okay, here's our like linear algebra bit. So let's associate permutations with vectors. So we're going to have these two vectors, x and y, going along. So they're both indexed by permutations and array notations. So let's say that if you have a permutation sigma, the x vector and the y vector associated with it is just x sub sigma 1 and on up to x sub sigma n, and similarly for y. And I don't know if this example is useful, but yeah, this is colored indexing. I hope somewhere further down I have a more sensible example with actual numbers. But yeah, this is just setting up vectors associated with permutations. And tau inverse simply denotes the inverse permutation corresponding to tau. And what we would be interested in is this particular product. Okay, so this is x sigma transpose multiplied by y tau inverse. So sigma and tau are not the same permutation in general, but and that's going to be kind of relevant in just a bit. But hopefully notationally, it's clear that when you take the product of these two vectors here, right, what you end up with is a polynomial, is a multivariate polynomial. Now this is 2n variables. So you have n x's and n y's, and the total degree is 2 because every term is a combination of one x variable and one y variable. So is this is the notation of the x and y vectors and what this product looks like, is this clear? Then I'll move on, but let me know if anything about this looks fishy. Okay, thank you. So moving right along then. This is just an example. So if you had sigma being 3, 2, 4, 1, then notice that the x vector associated with that would be x3, x2, x4, x1. And we have tau, which is 2, 3, 4, 1. So tau inverse is going to be 4, 1, 2, 3. You can just validate this if you like. So with tau inverse, we are going to have y4, y1, y2, y3. So that's the product that we're looking at. Okay, good. So that's just a sanity check example. And now we are going to be interested in we're going to be interested in understanding why these vectors relate somehow to compositions. Okay. All right. So first of all, notice that this y terms are nicely spread out across the individual summands, right? So y1 occurs exactly once, y2 occurs exactly once, and so on. And now let's think about where is y1? Okay, so think of which, for which index k does tau inverse send k to 1, right? Because that's where we're going to see y1, right? Because remember, y was just, if I am y1 and in the y vector somewhere I see y1, well, that's wherever the permutation took value 1, right? So that's, hopefully this is clear. So there's some k for which tau inverse of k is 1. So that's going to be y1 just by definition, right? So now k is therefore tau of 1. That's k, right? And so because we know that this is the kth term, right? We know that again by definition, the index for the partner x variable is sigma of k. Is that fine? Because x, we are doing x of sigma, right? So remember, what was x of sigma? X of sigma was simply x sub sigma of 1, x sub sigma of 2, and so on. This was x of sigma. So I know that y has, well, if I know that y1 is the kth, it's the kth index in this summation. So I know that the x partner that's there with it has an index of sigma of k. Let me know if this is reasonable, if it's making sense. This is just tau inverse of k is just a rewriting of y1. I'm just saying that, well, I know that 1, and I mean, there's nothing special about 1. You could pick your favorite index, but we work with 1 just to make things concrete and to try and get some visibility on what this has to do with compositions. Okay, so I'm just trying to read off y1 in terms of its actual semantics. So I know that, so if you go back here, we know that the ith term in this summation, right? The ith term in this summation is x of sigma of I and y of tau inverse of I. So if I know that this is tau inverse of k for whatever k, then I know that at x also I have sigma of k. Is this okay? Or, I mean, or is this confusing? And okay, I should have got this in the chat earlier. Sigma of tau of k, exactly. That's the intuition for why compositions now come in, because now we know that k is tau of 1. So we can plug that in to realize that the index of x is actually capturing the composition of sigma and tau. I really did think about whether we could build up to this and reverse engineer it, but okay, that's not something that I was able to do, but hopefully in retrospect, we see that compositions pop up quite naturally here, right? So the term with y1 is x sub sigma of tau of 1. Is this clear? Because then this hopefully establishes some intuition for what all this vectorization has to do with compositions. And in general, if you have yi, the x partner sitting there is tau of sigma of I. So give me a +1 if the slide so far makes sense. Okay, thank you. If anybody wants me to repeat anything, let me know. But this is really symbol pushing. I mean, just ask yourself where anything is and rewrite it in terms of what its definition was. So for example, if you want to look at y2, well, what was y2? It's, well, tau inverse of...
So there's something wrong with that sentence there. Y1 is x of sigma of tau of 1. But then when you go to yi, it becomes tau of sigma of I.
Oh, no, sorry. I think I may have swapped those when I was writing this out. I think it's supposed to be exactly the same. So that should be, I think the tau is inside, the sigma is outside. Thank you. I think that's sufficiently... Okay, I'll just in the meantime wait for folks to confirm that this is reasonable. I think I have a couple of +1s. I'm tempted to believe that this is making sense, but I'm also very tempted to fix this typo. Okay, the only thing is this tends to slow the browser down, and there's a bit of a spoiler as well. Oops. Okay, the spoiler is not a serious one. It's just everything we've said so far. So yeah, I mean, essentially, the x indices here. So in this product, so if I'm interested in capturing sigma composed with tau, right? I write down this product of these two vectors. I combine x of sigma with y of tau inverse to ensure that the x indices are capturing the composed permutation. Yeah, is this okay? I think if we were good up to everything that was said up to the previous line, we're good further along, I think. And yeah, thanks, Vinay, for pointing out the correction there. So hopefully this is now sensible. Yeah, so what I was going to say is, just as a quick recap, I mean, we worked this out for 1. If you want to work it out for 2, you want to look at, well, where is y2? And well, that's the third index here. So I'm going to look at, okay, I'm going to look at, well, who is tau inverse sending to 2? That, as expected, is 3 is going to 2 under tau inverse. And so basically, we have sigma of 3 sitting here, but 3 is tau. I mean, 3 is basically tau of 2 here. So you're basically getting, oh my goodness, that's completely illegible. But okay, hopefully you get the spirit of how this calculation is going. But yeah, the idea is, this is everything that we said for 1 works out for your favorite index. In particular, it works out for all indices. And that's why in this sum, what the indices of X are capturing is basically the values of the composed function, sigma composed with tau. So since I'm not hearing any complaints, I'm not seeing any complaints in the chat, I'm going to assume that we are good. And so we're making some progress. These vectors somehow are manifesting compositions for us. And now we want to count compositions. So basically the idea is to observe that if you have 2 compositions that collide, right, the ones that basically don't contribute any extra to the count that we are interested in, then these 2, the corresponding polynomials become basically equal. Okay, and that's straightforward in the sense that we know that X sigma 1 transpose Y tau 1 inverse is basically capturing rho 1, which is sigma 1 composed tau 1. So that's what the indices are going to be in this polynomial. And in the second polynomial, the indices are going to come from rho 2, which is sigma 2 composed with tau 2. So if these 2 compositions are essentially the same permutation, then they're going to manifest the same polynomials. Okay, so this seemed like a transparent enough statement that I've not added any more justification. Give me a +1 in the chat if this makes sense. If you have the same composed permutation, like if 2 pairs of permutations composed to give you the same permutation, then as polynomials, they're going to manifest as the same polynomial, just because of what we have already said about what these polynomials look like. Yeah, let me know if this makes sense, because this is going to be the engine of, what we are going to do next. Okay, very good. So then we can move on. And basically, we are going to, let me just, this, I don't know why this came through as a wall of text, but okay, let me maybe skip ahead and show you a picture. So I want to set up these matrices here, X transpose Y. So basically in X and Y, I have columns corresponding to all my permutations. So I'm going to have M columns and N rows in both X and Y. Okay, so I should have really done this probably with actual numbers, so sorry about that. But anyway, for some time I was just fascinated with little colored boxes. But the dimension of X is N times M, right? N rows because these are all permutations of 1 to N, and M columns because I have 1 column for every permutation in P, and there are M permutations in P. So Y is also N by M matrix. X transpose is a M by N matrix. So what happens when I multiply X transpose with Y? What is the ijth entry of X transpose Y? Well, let's think about this. The ijth entry is what? The ith row in X transpose. That's the scalar product that we've just seen. So hopefully this is not too hard to understand. So the ith row of X transpose, which is really the ith permutation in my collection, right? Colliding with or getting multiplied with whatever the jth column in Y, which is the jth permutation in my collection, right? So this is the scalar product. So the ijth entry in X transpose Y is the scalar product of the ith permutation and the jth permutation, right? And yeah, Janki is already suggesting that this is capturing the composition of these two permutations. And indeed, we are taking this scalar product, which we know corresponds to a polynomial whose indices are organized according to the composition, right? So do we agree that the number of distinct entries, the number of distinct polynomials in this matrix product is what we are after? That's the number of distinct permutations in P composed with P. Yeah, because the ijth entry in this matrix is the polynomial corresponding to, the product of, okay, maybe I should, sorry. I think, did I just say that Y is all the permutations? No, what do we want? We want the ijth entry to reflect the composition, exactly what Janki said, the composition of the ith polynomial and the jth polynomial. So of course, I'm not going to get that if I multiply X of sigma I with Y of sigma J. What should the columns of Y be? Maybe let me ask this just to sanity check. But we can reverse engineer what we want here. What I want is that the number of distinct polynomials in X transpose Y gives me the number of distinct permutations in P composed with P, right? That's the answer that I'm after. We'll come back to how we compute it. Okay, we'll come back to that. But somehow I'm translating my original problem into a matrix product problem. But what do I want in my ijth entry? Like Janki is saying already, we want this to somehow reflect a polynomial that captures the composition of the ith permutation in my collection and the jth permutation in my collection, right? To make this happen, I already know that if I multiply the X vector associated with Pi with, I guess I should put a transpose there. With what? If I multiply this with the inverse of Pj, right? Then this somehow corresponds to the polynomial that gives me the composition of Pi and Pj. Does that make sense? Yeah, okay. So for those of you more comfortable with notation, maybe let me just go back to the slide which had the wall of text and we'll just verify what we just said. Okay. So in X, the columns are going to be X sigma J, where sigma J is the jth permutation in my collection. And in Y, the jth column is going to be sigma J inverse. Okay. I accidentally, when I skipped to the picture, I think I may have just said that X and Y are the exact same matrices. They're not. Y has to collect the inverses because of our basic setup. In the ijth entry, the matrix product X transpose Y has this guy. And this guy is basically reflecting the polynomial that captures the composition between sigma I and sigma J. Okay, so because of what we have said about how pairs of permutations that compose to give you the same permutation also manifest the same polynomial, we know that we are only looking for the number of distinct polynomials in our matrix product. Okay, so our problem basically boils down to counting how many distinct polynomials are there in the matrix product X transpose Y. And if you're wondering if we have gone from something that was fairly straightforward to do to a messier situation, because now instead of counting, just compositions of permutations, suddenly we have to check if some m squared polynomials, we have to deduplicate a list of m squared polynomials, and that also after computing a matrix product where the entries are polynomials. So it all looks messier. So if you have that complaint, I'm totally with you. But at least does the claim make sense that if you somehow had this matrix product, and if you could count how many distinct polynomials are sitting in this product, that's exactly the count of the number of distinct compositions that there are in P composed P. Give me a +1 if that statement makes sense. Okay, good to know. Thank you. All right. So, and also if this is not clear to somebody, then please let me know as well. I'm happy to repeat any part of this. Like I said, I neglected to emphasize in my first shot that Y was collecting the inverses. So sorry about that, but Y is collecting the inverses just so that we get what we want based on what we know about how these products were set up, right? Okay, good. So that's what we have. Now for the clever bit. The clever bit is to say that we are not going to have to evaluate. So if we just try to do a product of polynomials and then try to come up with, well, how many distinct polynomials are there? That's going to be pretty heavy. And if we do that naively, okay, excuse me. If we do that naively, that feels like it's going to be as expensive as what we started out with. So we're not going to do that. Instead, we're going to try and evaluate these polynomials at random points and hope that somehow we get to the right answer. So let's see where this can go wrong. Okay, so let's think about this. So this is this is a suitably chosen space from where we are going to be, where we're going to let our polynomials take values. We'll see that this number, this arbitrary looking number is chosen carefully to achieve a certain probability of success. So you can ignore the 4n squared detail for now, 4n to the 4th detail for now. We're going to come back to that. But basically, pick values for your xi's and yi's. Remember that our matrices are basically a collection of 2n variables, right? So X has the X transpose matrix is n of those variables, so Y has the other n. So pick values for these variables uniformly at random from 1 to S, where S is suitably large space. And pick these values uniformly at random and independent of each other. Okay. And now as expected, we're going to substitute Xi. We're going to substitute for Xi with AI and for Yi with Bi. So now we have two matrices with numbers, okay? And so this is much less scary than multiplying them out as variables and being stuck with these long polynomials. Now these are just numbers, and you can multiply them as you would multiply regular matrices. And now what's the hope? The hope is that, well, so now you have a collection of n squared numbers. Just compute how many of them are distinct, and that's going to be the answer that we return. So let's stare at this for a minute and think about what could go wrong, okay? Can we ever overestimate the size of P composed with P? So can we, suppose P composed with P truly has, I don't know, so let's say P was 5, we said it can have at most 25 things. Let's say it actually has 20 permutations. One question to ask ourselves is, can our algorithm report more than 20 permutations? Right? I suppose the question is, what is the danger? Can it overestimate or can it underestimate the true answer? So if two polynomials are the same, right? If two polynomials are exactly the same, and we have, so these are two polynomials over 2n variables, and we evaluate it at some randomly chosen location. right? I've randomly picked variables, values for my 2n variables, and I have two polynomials that are completely identical. Now, no matter where I evaluate it, can I get different values for these polynomials? Remember that I'm evaluating them at the same place. No, right? So if two polynomials are the same, they will never report distinct values, right? But if two polynomials are different, right, can they end up manifesting as the same value at a random point? So for instance, I might have x1, y2 plus x2, y1. And I might also have x1, y1 and x2, y2. These are two different polynomials. And presumably they're coming from two different composed permutations that were actually distinct. Now, you can imagine picking values. This is maybe a silly thing to do is to pick the same value for, all the four variables. So although the two polynomials were actually distinct, they ended up manifesting as the same. And there could be there could be less silly examples of this kind of an error. So this is what I'm afraid of. I'm afraid that two things that were actually distinct in the matrix, in the product matrix, when evaluated at a random point, actually manifest as being the same. So they were actually different, but they ended up colliding and being the same. Whereas I'm never worried about two polynomials that were the same because they will never manifest as being distinct, right? So our final answer, is it going to be an underestimate or an overestimate of the true answer? So everything that had collapsed, all the compositions that actually were the same, will actually end up being the same polynomial, and they will never get distinct values, right? So exactly. So if anything, what might happen is that distinct compositions report the same value. So we might fall short of the correct estimate, but we will never overestimate, right? So our final answer is at most the true answer. We'll never overshoot it. But the question is, how often do we actually get to the right answer? So this is our claim. The output is never larger than what we want. And with probability at least half, it's actually equal to what we want. And let's just make that argument now. Give me a +1 if the underestimate part is clear. It's certainly clear to Janki because she came up with the answer. Can some of the others let me know if this is clear? Okay, thank you. All right, good. So now we want to say that we don't fail too dramatically. Okay, all right. So this is the underestimate part. So now suppose we have two distinct polynomials. We have to worry about these fellows, right? Because they might collapse. They might collapse at a random point when you're looking at it through the lens of a random evaluation. If you look at the difference of these two polynomials, it's a non-zero polynomial of degree 2. Now, what do we know about non-zero polynomials of degree d? We know that they cannot have too many zeros, right? Because they're non-zero. So from Schwarzschild, we know that if you have independent random values, right, then we obtain a 0 with probability at most 2 over s. Remember, this was d over the size of s. So S was a randomly chosen set from which we are taking values, right? S was a fixed subset from which we are randomly picking values. So our probability of error is at most d over s, d over the size of s by Schwarzschild. And because we have chosen s to be, okay, I think that bit is gone from the slides, but if we go back, we can confirm that we had chosen the set from which we were sampling to have 4m to the 4th many elements. So the probability that one pair collapses, right? Because that's, what does it mean that two distinct polynomials manifest the same value? It means that we have hit a 0 of the difference polynomial, right? Because again, so let's say we have two polynomials, let me call them P and Q. P and Q were distinct, but when I evaluated P at this thing, it ended up being equal to Q at that. So P and Q ended up being the same under this random evaluation. So P equals Q. at this randomly chosen point. But if p equals q, that means that p minus q equals 0. So that means that we have hit a 0 of the difference polynomial. But the difference polynomial is a degree 2 polynomial. So we can apply Schwarzschild to see that the probability with which we hit a 0 of the difference polynomial is at most 1 over 2 to the m⁴ths by the choice of the size of S. Now, this is one collapse, right? But we could fail if we collapse anywhere, right? I mean, so a failure is a failure if any two things that were supposed to be distinct manifest as being the same. So, yeah, any two distinct entries become equal with low probability. And how many pairs of distinct entries do we have to worry about? Well, X transpose Y is a M by M matrix. It has M squared entries. So the number of pairs that you can form with M squared entries, so these are the things that you have to worry about, whether they remained distinct or not. I think that's M squared choose 2, but yeah, that's upper bounded by M to the 4th, right? So you cannot have more than M to the 4th pairs of distinct entries to worry about. And therefore, I mean, what's the probability that you fail even once, right? That's basically no more than M to the 4th divided by 2M to the 4th. And so that's half, right? So basically we are saying that one pair fails with this extremely low probability, right? And so now we are just upper bounding that, okay, a failure for us is a failure at any one of these pairs. So this would be, is this what we would call an union bound? We are saying that, well, we're basically trying to say that, well, none of these bad things happen with probability at least something, or any of these bad things happen with probability at most something. So we are adding up these probabilities of the bad things happening and saying that, well, you know, that overall bad event happens with probability at most 1/2. So the good thing that nothing, no collapses happened at all, happens with probability at least 1/2. And of course, if you're paranoid, you can take this relatively efficient algorithm and repeat it as many times as you want to boost the success probability as much as you like. So if you repeat this whole algorithm k times and take the best count that you get, right? Because we are consistently underestimating. So pick up the largest count that you get over all your experiments. And the probability that you're still underestimating will be at most 1 over 2 to the k, because that would mean that you had a failure event in each one of your experiments, and that would happen. So that failure probability goes down exponentially with the number of repetitions that you give yourself, right? So that's kind of the algorithm. And actually, that's all that I put on the slides. Ideally, I should have also worked out the running time for you, but well, let's look at it. The running time is really, is this in a sense hashing? In some sense, yeah, I guess in spirit, this is what we're saying, that collisions don't happen frequently. But yeah, in some sense, yeah, instead of multiplying permutations directly or multiplying polynomials directly, we are mapping it to a number and hoping that distinct polynomials survive as distinct numbers. And yeah, with hashing, the bad event is when things collide when they're not supposed to. And that's what's going on here in terms of, that's what we identify as the bad event and we bound the probability of. And I think the fact that we're coming from polynomials is useful because our collision event can now be regarded as hitting the 0 of a low degree polynomial. And we set up our independent random events to be such that Schwarzschild played nice and gave us a nice probability of success or a low probability of failure. But yeah, I think we do want to also say that we have done something non-trivial over our baseline. The idea is that all the computation here basically boils down to matrix multiplication. So we are multiplying two n by m matrices with entries from 1, 2, and so on up to m to the 4th, right? And that's Yeah, so I think in the miniature, if I remember right, they say that, well, for convenience, let's assume that we have n permutations, so m equals n, and that allows you to say that matrix multiplication, that only takes you n to the whatever the matrix multiplication constant is, and that's definitely an improvement over if you did the brute force algorithm with n permutations, you would be looking at n squared time just to generate all of them. Just to go over all pairs, and then to actually generate the composed permutation, that would be another n. So you're looking at n cubed. So now you've gone from n cubed to whatever time it takes to multiply two matrices, which is an improvement. I think it's worth checking what happens if you're looking at n by n matrices as well. But I think it's still going to be better off than the brute force that we started off with. But of course, you pay a small price in terms of having to deal with an error probability, but even a constant number of repetitions of this algorithm should boost your confidence quite a bit. So yeah, it's a super informal way of saying it. I'm sure you can say it nicer, but yeah, this is the thing with randomized algorithms. I think they tend to be pretty elegant, pretty fast. And yeah, I mean, the small compromise in terms of having to worry about the failure probabilities and so on. But here it all turns out to be quite reasonable. And I think it's just nice that, so the cleverness here is in being able to capture compositions with polynomials. And the rest of it, I think, is just really knowing how to leverage, like you said, getting this hashing idea to work by realizing that collisions correspond to hitting zeros of a non-zero polynomial with low degree. So yeah, so you can set up the space from which you sample from to have the right size so that you can reverse engineer the right success probability. So that's essentially what's going on. And yeah, I think that's pretty much it. So I'm going to try and see if we can continue our streak of finishing within the hour. It's still way over time relative to the original premise, but I think we've lost that a long time ago. But yeah, I think I will perhaps stop here. Maybe a good follow-up exercise is to go and work out some of the details, but hopefully the main gist of it was okay. Are there any other questions or comments?
Yeah, so one comment is it looks like you don't need the full power of Schwarzschild. You can prove this without Schwarzschild at all. So this looks like some old technique that comes from complexity. So effectively what you have is, the annotation is enabled.
Let me Pellet's annotations enabled. Can you use it?
Yeah.
Okay, good.
Yeah. So you have some xi, some yj or something, right? There's some polynomial of this sort, right? I'm just going to put a prime to indicate.
Right.
Yj prime, something, right? So when there's collision, you have something of this sort, right? And you want to, we were using Schwarzschild and we said this is degree 2 and so on. So instead of doing all that, you keep y1 aside, right? Don't assign anything to y1, but assign everything else.
Sure.
If you assign everything else, then you would get some constant times y1 on this side plus some alpha 1 y1 plus beta 1. On this side, you'll get some alpha 2 y1 plus beta 2. Right? And so you'll get y1 as some rational number.
Correct.
Okay. If it's a rational number, you're never going to get it anyway because all your numbers are integers technically, right? You're never going to hit this. But if it turns out that it happens to fall nicely in that interval of 1 to s, I think you had, then of course you indeed have hit. You would get a collision, right?
Correct.
So let's assume that you don't get the sort of bad rational number, but you actually hit something here. Then the probability that happens, now you choose a y1, right? You're choosing y1 uniformly here. The probability that y1 that you choose actually happens to be this is 1 over s.
Oh, I see. Great. Yeah.
Okay. And that is that's better than the 2 over S bound that you get from
Yeah.
Schwarzschild.
Yeah.
And so I sort of realized that probably, I don't know if there's any paper I hadn't thought of this. Maybe Schwarzschild is probably easier if you have multilinear polynomials or something like that. I'm not quite sure. Yeah. So this clearly is multilinear because you have x's and y's. You never have a copy of x square and so on, right?
Correct.
You never get that. You always get an x and a y. So
That's
this
true.
is multilinear. So maybe there's a better bound for multilinear. But in any case, you don't need
You don't need it at all.
Schwarzschild. Yeah. The moment you put it up, I mean, this is a proof that
Okay.
I was constructing when you were doing, and then I was a bit surprised you went to Schwarzschild. Yeah. So.
Yeah, no, this is very cool. Okay.
Okay.
You just doubled our probability of success, I guess, or reduced
Yeah.
our
So this is some old Rasparov stuff. Yeah.
Oh, I see. Okay, that's very nice to know. And it's the first time I'm seeing something like this. So yeah. And maybe technically not, but given my memory, this feels fresh. So thank you. I don't have an immediate recollection of an argument of this style, but it's very useful to isolate your favorite variable and then do this argument. Yeah, super nice.
Yeah, right, but it only saves you a factor of 2 in the size of S or something, right?
Yeah,
doesn't do much, but anyway.
Yeah, but more than the saving, I think the argument becomes now a little more self-contained as well. I think this is just this is just really sweet. Yeah. Okay, so yeah, super nice. Thanks, Vinay. And I don't know if there was anything I missed in the chat. Hopefully not. Yeah, Jagdish, I'm just going to think a little bit offline about your renaming argument. I think that seems very fair, but it's just that yeah, I tend to be easily confused, so I'm just going to cross-verify that in just a bit. But yeah, it does seem like the true value is in the range of size of p squared, and this algorithm lets us hit the right value with decent probability. So hopefully we're all happy. And tomorrow we are going to be checking if a binary operation is associative or not. And it's the same. The story seems to have a similar narrative. We'll start off by saying that the brute force thing is to just check associativity by brute force. But then by a slightly differently flavored construction, we are going to transform things. And again, if I remember correctly, again, leverage this Schwarzschild kind of idea. So that's coming up tomorrow. So see you at 10 once again. Thanks so much for coming and staying. Good night for now. See you soon.